He stands at the edge of nothing that can be walked to. Above him, the night is a slow ocean of black, salted with light that left before language. The question is older than astronomy and younger than every breath. If he sails long enough, where does the water of space meet ashore? He watches Andromeda, a smear of ghosted silver, and imagines moving toward it for 1 trillion lifetimes, through cold that deepens, through distances that multiply as he crosses them. The map always redrafts itself under his feet. Horizons slide away like mirages. The universe expands not as a stage, but as the stage itself learning new steps. He was told that everything must have an edge, cups, continents, childhood. But when the mind turns outward, edges turn to rules. Relativity says geometry is not background but actor. Quantum theory whispers that emptiness sees. Beyond the farthest galaxies, beyond the fossil light of the first fire, lies either more of the same, folded or infinite, or a frontier that cannot be crossed not because there is a wall, but because the wall is time itself. If there is an end to space, it may be a kind of silence, a horizon where events can never speak to us again. If there is no end, then we live inside an endless sentence, and our task is to learn the grammar. The camera floats upward, into the dark between the stars, then further until filaments weave like tendons across a cosmic skull. The narration softens. There is a boundary he cannot walk to, only infer. He will not find it with a compass, only with a principle. Tonight he asks the oldest modern question, not how the cosmos began, but where it stops, if it stops at all. They began with a horizon made of thought. In the echoing halls of early philosophy, the pre-Socratics set the question like a stone at the center of a still pool and watched the ripples circle outward. Some, like Anaximander, spoke of the apeiron, the boundless, an origin without rim, a principle without edges. Others imagined layered heavens, nested shells in which stars were not scattered but fixed into crystalline spheres. Aristotle would carry this vision to its most influential form, a cosmos finite in size yet complete, embraced by the outer sphere of fixed stars. Beyond that vaulted shell, he allowed no void at all. An edge existed only as the terminus of nature. Outside, there was not a different kind of space, but the absences of the very notions that define inside. The world was full, finished, and closed. Centuries later, that calm enclosure trembled under questions that could no longer be sealed within any firmament. Medieval scholars argued over a silent frontier. Was there a void beyond the stars, a region unlit by God's lamps, or would such a void tear logic itself? In cathedral schools and private letters, the debate unfolded with careful metaphysics. If the firmament could be pierced by thought, would motion beyond it be possible, and relative to what? Some theologians allowed that an infinite void, if it existed, would still be held in the hand of the divine. Others held that a world without walls required a new grammar entirely. The heavens themselves became the argument, no longer a ceiling painted with constellations, but a proposition about what it means to have a border. In the 18th century, Immanuel Kant drew the problem into the geometry of reason. He set forth the antinomies, rigorous arguments that the world must be finite in space, and equally rigorous proofs that it must be infinite. Each conclusion locked into contradiction with its twin. The impasse did not settle the cosmos. It calibrated the limits of pure reason confronting magnitude. Whether space extends without bound or curls back on itself, he suggested, may be a matter not of intuition but of the conditions under which intuition is possible. The question of an end to space had crossed from architecture into epistemology. It would return to physics, when physics acquired the tools to measure the sky with clocks and rulers tuned by the universe itself. Newton provided the stage on which the next act would play. In his Principia, space is absolute, a vast and indifferent arena in which bodies move, forces act, and time meters their changes. The stage itself does not answer, it only is. But by setting the theater infinite and the stars ageless, Newton seeded a disquiet that would become a famous paradox. If space is endless and uniformly filled with luminous suns, then the night sky should blaze as bright as a stellar surface in every direction. The darkness that soothed the human eye became a scientific indictment. Either the distribution is not uniform, or the stage is not ageless, or the light is not able to arrive. Later attributed to Heinrich Albers, the paradox had been noticed by Kepler and Chesso. It waited for a cosmos with history to dissolve it. Another disturbance arrived from a principle whispered rather than codified. The suggestion, associated with Ernst Mach, that inertia might be determined not by local emptiness but by the mass of the entire universe. If the resistance to acceleration is a relation to everything, not a solitary property, then perhaps space is not merely the hall in which motion is measured. Perhaps the hall itself leans when the dancers move. The yearning to tie local mechanics to cosmic totality prepared the imagination for what came next. Albert Einstein turned that yearning into equations. In 1917, only 2 years after general relativity had bent the path of light around the sun in his field equations, he applied the theory to the universe as a whole, to keep the cosmos static, because the literature and the eye imagined it so. He introduced a new term, the cosmological constant lambda, and found a solution with positive curvature, a closed, finite universe with no walls. Like the surface of a sphere, the three-dimensional space of this model loops back on itself. Travelers can circumnavigate forever without finding an edge because none exists. Finite, yet unbounded, an audacious answer to Kant's puzzle, written not in syllogism but in geometry. In this first relativistic cosmos, where space ends is the wrong kind of sentence. There is only continuation, returning in grand arcs. But the equations would not sit still. In 1922 and 1924, Alexander Friedmann discovered that Einstein's field equations admit expanding and contracting solutions without the cosmological constants balancing hand. The curvature could be positive, negative, or zero. Each geometry implies a different global fate, but none requires a boundary. Georges Lemaitre, priest and physicist, would connect the mathematics to the sky itself. In 1927, he suggested that the redshifts of spiral nebulae, their spectral lines stretched toward the long wavelengths, signaled not their exile from a central explosion, but the expansion of space carrying them. In 1929, Edwin Hubble published the linear relation that would bear his name. The farther a galaxy, the faster its recession, a simple law written across millions of light years. Distance had become speed, not because the galaxies powered themselves away, but because the fabric between them lengthened. There was no center, no embankment to stand upon and watch the river flow. The river was the coordinate system itself deepening. In a universe with a past, darkness acquires a reason. The night sky is dim because the stars have not been shining forever, because dust does not have time to glow to equilibrium, because the light from the farthest regions has not yet reached the present shore. The paradox dissolves in history. An edge appears, not as a wall in space, but as a horizon in time. That horizon was photographed by accident. In 1964, Arno Penzias and Robert Wilson tuned a horn antenna in New Jersey to map faint radio signals. An irritation, persistent, isotropic noise, refused to vanish, immune to hardware adjustments, and even to the eviction of pigeons roosting within the feed horn. The signal was the cosmic microwave background, relic radiation, from when the universe was only about 380,000 years old and first became transparent. In that era, when protons seized electrons into neutral atoms, light decoupled from matter and began a long journey across expanding space. It cooled with the stretch and now arrives from every direction with a temperature near 2.725 Kelvin, a nearly perfect blackbody. The sky had become an archaeological layer, a surface of last scattering, not the end of space, but the farthest past that light can presently reveal. To this fog of ancient light, satellites added detail that would turn metaphysics into measurement. In 1992, the COBE mission announced tiny temperature anisotropies, ripples 1 part in 100,000, that trace the infant seeds of all structure. WMAP, launched in 2001, sharpened the map. Planck, launched in 2009, refined it further, extracting the power spectrum's acoustic peaks, whose positions and heights whisper the geometry of the universe. The first peak's angular scale told a precise story. On the largest scales we can observe, space is remarkably close to flat. Combined with other distance ladders, baryon acoustic oscillations rippling through galaxy surveys, Type Ia supernovae as standard candles, the data confined spatial curvature to values so small that, within the observable radius, the room appears Euclidean to better than a percent. Yet curvature is not topology. Even a perfectly flat space can be compact if its sides identify, the way a video game wraps the player from one edge of the screen to the opposite. Once the CMB had painted the baby picture, cosmologists asked whether the room is larger than it looks, or cleverly folded. They imagined multiply connected universes. A 3 torus where traveling far enough returns one to the beginning along a different path. A Poincaré dodecahedral space where 12 pentagonal faces meet with a twist, perhaps explaining the surprising calm of the largest CMB modes. If space wraps, the sky might hold signatures, pairs of matching circles where light has journeyed around the cosmos along different routes to the same observer. In the late 1990s, theorists formalized this circles in the sky test. In the decades since, searches with COBE, WMAP, and Planck have hunted for such twins in temperature and polarization. The results narrowed possibilities without closing the case. Many small, compact topologies are now constrained. If our universe is a torus, its fundamental domain, the smallest repeating cell, must be larger than the observable cosmos in most simple models, or the matched circles would have been seen. If it is the elegant dodecahedron, the twist and scale must be such that the imprints hide below current thresholds. Observations of polarization, less muddied by late-time astrophysics, promise a sterner test. Future maps will either reveal the faint symmetry of a wrapped space or push the fundamental domain farther beyond the horizon of verification. Between ancient spheres and modern satellites, the frontier migrated. Where early thinkers sought a wall, later observers learned to listen to boundaries set by causality and time. The discovery phase did not end in a cliff but in an atlas of horizons, particle horizons marking what has ever spoken to the present, event horizons in accelerating cosmologies, delineating what can ever speak, and the practical horizons of telescopes tuned to specific bands, each pushing deeper into a cosmos that may have no rim at all. The question, where does space end, survived its translation from poetry to physics by changing its tense. It became how far can events communicate, and how is geometry written into light. In this way, the pursuit of an edge produced a new kind of shore. It is painted not on the outside of the world, but across its memory. It is observed in microwave whispers, in the arrangement of galaxies along filaments stretched like tendons over billions of light years, in the gentle rhythm of acoustic peaks, in the absence of twin circles that would betray a hidden wrap. It is described by equations in which matter and energy do not fall through space but curve it, and by instruments that extend the human eye until it brushes the first transparency of the universe. The old antinomies softened into measurements. The medieval debate found a modern accent. If there is a beyond, it is not outside but earlier. And if there is a boundary, it is not a wall but a law. There is no wall, and yet there are limits. The shock begins with a simple measurement written into starlight. Distance in the universe is not a static ruler but a living quantity. When redshift is read not as a Doppler sprint through space, but as the elongation of wavelengths carried on a stretching fabric, a strange consequence emerges. The farther the galaxy, the faster its recession. At sufficiently great remove, the recession speed exceeds the speed of light, not by breaking a law, but by belonging to a different clause of it. Special relativity guards objects within space from outracing light. General relativity allows space itself to change scale. The boundary that intuition expected as a cliff becomes a grammar lesson. Velocities born of motion are limited. Velocities born of geometry are exempt. The numbers tie the lesson to scale. The observable universe, the region whose light has had time to arrive since the birth of transparency, is about 46 billion light-years in radius when distances are reckoned now, in proper terms. It is already larger than the naive product of light speed and cosmic age because space has been expanding during the journey. There is, then, a horizon that turns on history, not the end of space, but the edge of what has ever been in causal contact with the present. Beyond it, galaxies may exist in profusion, but their messages have not yet crossed the ocean of time. The night sky is not dim because stars are scarce. It is dim because time is young and geometry is dynamic. The astonishment deepens with a discovery made at the end of the 20th century. Type Ia supernovae, white dwarfs pushed to a thermonuclear threshold and used as standard candles, were found to be fainter than expected at intermediate redshifts. Teams led independently by Saul Perlmutter and by Brian Schmidt with Adam Rees interpreted the result. The expansion of the universe is accelerating. The cosmos is not coasting from an ancient push. It is being urged onward by something whose pressure is negative, whose effect is to make geometry speed up its own separation. The shorthand name is dark energy. In the simplest reading, it is Einstein's cosmological constant returned, a vacuum energy whose density remains roughly steady as space grows. With that return comes a new horizon, subtler and more final. In a universe dominated by such a component, a cosmic event horizon forms. It is not drawn on a chart with a pen. It is defined by the limits of communication in the far future. There exists a proper distance today, on the order of tens of billions of light years, beyond which events happening now will never, even with infinite patience, send signals that arrive. Not because their voices fall silent, but because the space between speaker and listener expands too swiftly for the sound to close the gap. This horizon differs from the particle horizon, which marks what has been seen so far. It differs from the Hubble radius, the scale of recession where the instantaneous rate approaches light speed. The shock lies in the multiplicity. Where a child imagines a single edge, physics replies with a hierarchy of horizons, each a different verb tense of possibility. What is spoken, what can speak, what can never be heard. If acceleration continues, the cosmos tends toward a de Sitter phase, an asymptotic condition in which the event horizon is as fundamental to the large-scale world as the event horizon of a black hole is to a collapsed star. In such a future, distant galaxies do not merely drift out of sight. They cross a causal line and cease to be part of any shared story. Their light, emitted later than a certain date, is forever quarantined beyond a border that no traveler can chase. Locally bound structures hold together, galaxies, clusters, the architecture soldered by gravity's patience, but the great web of filaments thins across the edges of knowability. The universe does not end, conversation does. The next surprise is linguistic. Geometry allows a space to be finite and edgeless. On Earth's surface, a journey westward can continue without a cliff. The finitude lives in area, not in borders. In 3 dimensions, a positively curved universe, a 3-sphere, achieves the same trick, a finite volume with no boundary to fall over. Flat space, too, can be compact if its opposite faces are identified, forming a 3-torus in which a long voyage returns to its start without ever meeting an outer wall. Here, the shock is philosophical as much as physical. The sensible categories of inside and outside depend on the topology as much as on the metric, and neither category promises a material rim. The mind that asks for a fence finds rules instead. The observational language hardens these ideas into constraints. Precision maps of the cosmic microwave background, its temperature ripples and polarization curls, fix the angular scale of primordial sound waves. Those acoustic peaks imply a near-Euclidean geometry on the largest scales accessible. Combined with baryon acoustic oscillation measurements in galaxy surveys, and with supernova distances, The inference is consistent. Spatial curvature, if non-zero, is small enough that within the observable domain the room is effectively flat. Yet flatness does not settle the question of infinite extent. The cosmos could be a vast torus whose fundamental cell is too large for any current test to circumnavigate. It could indeed be infinite. The shock, again, is epistemic. Observation can fence off what must be true inside the horizon of data. Beyond, many global possibilities remain logically open. Another layer of astonishment resides in velocities. The Hubble radius today, c divided by the Hubble constant, is a scale of about a few tens of billions of light years. At that distance, recession speed equals light speed, but nothing catastrophic happens at that shell. Photons emitted inside it can still struggle inward to reach an observer, while photons emitted outside may never arrive, depending on the expansion history. The speed limit that seemed absolute reveals itself as local doctrine masquerading as global law. The cosmos enforces causality with cones in spacetime, not with rails in space. The image of a wind-tossed sea replaces the image of a static shore. Boats may drift apart faster than oars can row because the water is flowing, not because the oars have failed. Acceleration adds a final irony. As the event horizon settles, the cosmic microwave background cools further. Its wavelength stretches beyond detection for any physical receiver not built from metaphors. Background sourced by local environments, starlight, dust, the hum of civilization, eventually drown the ancient signal. The deep past, which once defined the visible limit, slips beneath a thermal horizon of the future observer's making. Knowledge itself acquires a horizon defined by entropy and by isolation. The universe remains. What vanishes is the ability to know it as it was known. This is the fracture line that divides intuition from theory. The ordinary experience of edges, cup rims, shorelines, the outer skin of a fruit, teaches that limits are places. Cosmology replies that limits are conditions. The particle horizon is the condition of light's finite age. The event horizon is the condition of accelerated expansion. The Hubble sphere is the condition of the instantaneous rate at which rulers lengthen. None of these are barricades hammered into space. They are truths about which events can be braided into a common history. Where does space end? In this shock, the answer becomes stratified. It ends, for the purposes of seeing now at the particle horizon, a sphere defined by time. It ends, for the purposes of ever seeing at the event horizon, a sphere defined by fate. It does not end, in the sense demanded by hands that want to touch a wall, because the manifold may be without boundary even if it is finite, and may be boundless even if it is infinite. The question is not discarded. It is refined into several that can be asked cleanly and measured at least in part. The astonishment is that each refined question has a different, precise reply, and that none of those replies contain a fence line. Dark energy, whatever its essence, enforces the shock geometrically. If it is a cosmological constant, the horizon's area is fixed by a constant curvature. If it evolves with time, horizons breathe, and the inventory of what may be known changes accordingly. If the equation of state parameter slips below -1, a phantom regime threatens the coherence of structures in the unimaginably distant future, tearing even molecules and atoms as the scale factor accelerates to a catastrophic pace. If the vacuum is metastable, a transition could redraw the map in an instant as a bubble of lower energy races outward at nearly light speed, repaving the laws themselves. These possibilities are not prophecies. They are branches permitted by equations tested in other domains. Their drama is the corollary of a simple measurement in supernova light and microwave patterns. Nothing in this shock requires a metaphysical leap. Everything in it asks a metaphysical temperament to accept a new kind of edge. The viewer of the sky is left with a picture that refuses to be framed. The frame is replaced by a set of horizon conditions, each grounded in data, each coherent with general relativity's grammar of curvature and causality. The world does not end in a line. It ends, provisionally, in what can be exchanged. Space is not a container that runs out. It is a relation that changes character beyond certain scales and times. Thus, the scientific shock is not a drama of overthrow, but of translation. A child's question meets an adult's language and finds that the answer is subtler than yes or no. Where space ends depends on what is meant by end, by space, by where. And the astonishing part, the part that belongs to the closing minutes of the century that discovered acceleration, is that while those meanings are intricate, they are not arbitrary. They are printed in the sky, in the faint blue-red map of the first light, in the standardized explosions of dying stars, in the gentle slosh of galaxies on acoustic scales. The edge the mind sought is present, but as a horizon. It moves with time. It answers to law. And in that recognition, in that quiet, disciplined awe, the shock becomes the beginning of understanding. The sky becomes a ledger, and the instruments learn to read it. What began as a question about edges settles into a program of measurement. Weigh the geometry, trace the web, photograph the first light, and test whether the room itself folds back upon its occupants. Telescopes and satellites turn darkness into data. The universe replies in harmonics, in ripples of matter and light that travel together but speak in different registers. On the microwave background, the earliest music is scored. Tiny fluctuations in density, seated in the primordial plasma, set off sound waves that rang through the young cosmos until atoms formed, and the medium turned transparent. Those waves froze into a pattern that still hangs across the firmament, a faint modeling in temperature and polarization. The angular size of the first acoustic peak, measuring roughly the scale that sound could cross before recombination, lands near a degree on the sky. Interpreted through general relativity and the known physics of radiation and matter, that measurement acts as a ruler thrown into three-dimensional space. It says that on the largest scales measured so far, spatial curvature is exceedingly small. If the cosmos curves at all, the bend is gentle. The Great Hall looks Euclidean within the observable sphere. The numbers hide few surprises. Estimates of the curvature parameter cluster near zero, with uncertainties tightened by the careful marriage of data sets, microwave maps, galaxy clustering, supernova light curves, each contributing a separate angle on the same geometry. A second ruler checks the first. Long after the plasma cooled, the same acoustic physics left an echo in the arrangement of galaxies, the baryon acoustic oscillation. This feature, a preferred separation on the order of hundreds of millions of light years, sifts through redshift surveys like a watermark. When plotted as a subtle bump in the correlation of galaxies with one another, it confirms distances and expansion histories drawn from the microwave sky. Layer by patient layer, surveys have traced this bump across cosmic time, watching the hallmark separation lengthen in comoving coordinates as the universe grows. No cliff appears, only calibration. The scale links nearby galaxy maps to the near-infinite hush of ancient radiation, and both link to a model in which space, if not exactly flat, refuses dramatic curvature. Light is not a passive witness. As it crosses the cosmic web, it bends in deference to gravity, and that lensing, once a theoretical subtlety, becomes a tool. Weak lensing, measured statistically by the slight, coherent stretching of galaxy shapes, draws maps of mass rather than only of starlight. Those maps reveal filaments like stretched tendons, clusters like knotted joints, and voids like hollows where structure is thin. When compared with the acoustic rulers, lensing tests the balance of geometry and growth, how fast the universe expands, and how quickly matter clumps in its wake. The agreement is not a chorus without discord, but the notes share a key. The shape of space, as inferred from early light, has a cousin in the late time distribution of mass, and the cousin's face is recognizably similar. The investigation then asks a more intimate question. Does space repeat? If the universe is compact, if its global topology stitches opposite faces together, then the sky might show echoes of itself. The circles in the sky, proposal imagines that light could take multiple routes around a wrapped cosmos to reach the same observer, painting paired, matched circular patterns in the microwave background. Searches for such twins in temperature maps have come up empty within the sensitivity and angular resolution achieved so far, pushing the minimal size of any compact fundamental domain beyond the diameter of what can be observed. Polarization, less muddied by late-time astrophysics, offers a sharper chisel. Analyses there, too, have not uncovered the neat symmetry of a small, closed fundamental cell. The absence is not proof of infinity. It is a constraint that the room, if wrapped, is wrapped at a scale too large for present eyes to circumnavigate. Topology retreats beyond the horizon of current verification, but not beyond the horizon of logic. Between those grand tests, the cosmic web speaks in its own language. Redshift surveys follow hundreds of millions of galaxies, measuring their positions in space and their motion with respect to the Hubble flow. Structures thread together into a foam of filaments and voids, clusters and superclusters stretching over hundreds of millions of light years. In peculiar velocities, departures from pure expansion, gravity's hand is traced. In redshift space distortions, the rate at which structure grows under that hand is inferred. The maps do not terminate at an edge. They fade at the limit of the survey's depth, a practical boundary rather than a physical one. Yet within the reach of fiber-fed spectrographs and panoramic cameras, the same story repeats with variations. Standard rulers agree with each other. Growth follows a pattern consistent with the background geometry that the microwave sky and supernovae have measured. At the far end of sight, newly built eyes adjust to darkness that existed before galaxies matured. Deep fields stare into apparently empty patches for days and weeks, stacking photons until the earliest structures surface. Through these windows, Hubble sketched a ladder of galaxies receding to high redshifts. New infrared observatories refine and extend that ladder deeper, into an era when stars were first lifting the fog of neutral hydrogen. Candidates at redshifts above 10 appear as tiny, reddened smudges, their light stretched by expansion into the infrared bands. Spectroscopy chases confirmation, teasing apart genuine distance from the tricks of dusty, less distant interlopers. The work remains delicate, but the trend is not. Even the earliest times accessible show that structure developed rapidly under gravity's slow insistence, and that the timeline of reionization, when the first luminous objects carved bubbles of transparency in the cosmic medium, was neither instantaneous nor glacial. The edge glimpsed here is not a rim. It is the last scattering surface receding in time, its afterglow cooling as the universe expands. Anomalies, too, become part of the record. On the largest angular scales in the microwave background, alignments of low multipoles have tempted speculation. A cold spot, statistically unusual yet difficult to declare unique, sits like a bruise in the map. The quadrupole and octupole show a shy preference for a shared axis. Are these flukes in a universe where randomness must produce curiosities, or do they hint at physics not yet folded into the model? Perhaps a subtle topology, perhaps an imprint of large-scale structure through the integrated Sachs, Wolf effect. Surveys have sought supervoids that might explain temperature depressions via evolving gravitational potentials. Candidates exist, but the case remains cautious, the statistics disputed. The discipline of the field is to weigh charm against certainty, and to let time multiply the data until the balance tips. The investigation also telescopes inward, into the parameters that define the concordance model. Baryon density, cold dark matter density, the amplitude and tilt of primordial fluctuations, the reionization optical depth. Each is measured independently in multiple ways, cross-checked where degeneracies could mislead. The resulting picture is spare. A universe governed on the largest scales by general relativity, filled mostly with components not yet directly identified in the laboratory, expanding from a hot, dense origin, with structure grown from nearly scale-invariant seeds. No perimeter is drawn by these numbers. What they provide instead is an atlas of distance-redshift relations and a grammar for horizons. How far the past extends into the present's light, how far the present can lean into the future's communication. Even the silence between features becomes informative. The lack of matched circles at observable scales, the absence of strong non-Gaussianities in the primordial fluctuations, the uniformity of the microwave background to 1 part in 100,000. Each negative result is a boundary on possibility. Each is a wall to speculation, forcing topology to larger cells, compelling inflationary scenarios toward simplicity or toward delicate complexities that hide behind the veil of present sensitivity. In cosmology, absence is a measurement that narrows the maze by removing corridors. Lens by lens, ruler by ruler, the cosmos reveals that limits are phrased as horizons. The particle horizon, measured by the age of light and the speed at which space expands, marks the farthest layer that has ever spoken to the present. The Hubble sphere, c over the Hubble parameter, marks a scale where recession equals light speed, a diagnostic, not a border. The future event horizon, where it exists in models with accelerating expansion, is stranger still. It is a line drawn not around existing matter, but around the set of events capable of becoming part of any observer's causal past. Precision cosmology does not only map where things are, it maps which parts of the universe can ever exchange information. In that mapping lies the modern answer to the ancient question. If the old dream of a wall survives anywhere, it is in metaphors where images of ships and shores still serve. The measurements do not mock those images, they refine them. The shore is a time surface, the breakers are light cones, the tide is the scale factor rising. Instruments translate poetry into plots and then back again into understanding. The shock of the previous chapter, multiple horizons with different meanings, here becomes resolved into specific, testable patterns. Curvature is corralled near zero by acoustic peaks. Global wrapping, if present, is pushed beyond the portion of the universe that observation currently commands. The Webb's lensing verifies growth against geometry. Early galaxies flicker into the record at redshifts that stretch credulity only until spectra confirm their age. Anomalies are listed, not embraced, pending the expansion of the archive. With each new map, the implied edge moves, not because the universe changes its mind, but because the definition of edge is revised by knowledge. The program of deeper investigation replaces walls with numbers and numbers with laws. Where a medieval debate imagined a firmament that could be punctured by metaphysics, modern cosmology finds horizons that are not in space alone, but in the causal structure of spacetime. The search for where space ends becomes a catalog of how and when communication fails. And in that catalog, constructed from ancient light, from the marching of galaxies, from the curvature of faintly sheared shapes, the outline of the cosmos draws itself without resorting to a line that can be touched. It is an outline of possibility, measured, weighed, and left open at exactly the points where openness is honest. Acceleration writes an iron script across the sky. As dark energy takes command, the event horizon settles into place like a quiet, incurable boundary. It is not a wall that can be approached, but a condition that edits which stories can ever be shared. Each year, more galaxies cross that causal line. Their future light cones peel away from ours, thinning the braid of possible communications. The great web remains vast, yet its threads fray where fate forbids exchange. In the long arithmetic of time, clusters that are now neighbors become strangers. Superclusters loosen. What remains bound are only the most intimate congregations of gravity, galaxies, groups, the local island whose stars and dark matter have already pledged themselves to one another. Beyond the island's surf, the sea remains, but its waves will never reach the shore. This isolation is not a catastrophe, it is a theorem. In a universe that asymptotes toward de Sitter expansion, horizons acquire thermodynamics, with temperatures and entropies that behave like those of black holes, though spread over an immensity. The cosmos comes to wear a veil that is measurable in principle, impenetrable in practice. Evidence of the early universe. The microwave background, the baryon acoustic watermark, persists for a while as light within reach. Then wavelengths stretch beyond any practical receiver. Then nearby starlight and dust, and the activity of local civilizations outshine the ancient whisper. Cosmology's archive is not destroyed. It is sealed away by expansion. The mystery of where space ends is now tied to a quieter question. How much can be known before the sky stops answering? Amid this deepening solitude, a smaller dissonance becomes loud enough to matter. The rate at which the universe expands today, when measured nearby by constructing a distance ladder from parallax to variable stars to supernovae, lands higher than the rate inferred from the early universe's imprint on the microwave background, when that imprint is translated through the standard cosmological model. The disagreement, tiny in absolute terms, significant in precision, could be the signature of subtle systematic errors hiding in either rung of the ladder, or in the translation from early time physics to present-day parameters. Or it could be a hint that the model itself needs another sentence, a dark energy that changes with time, a softly curved geometry that current analyses have underestimated, an interaction that allows dark matter and dark energy to exchange influence. The tension refuses to declare its origin. It sits between data sets that are each internally coherent, each careful, and asks whether the universe is as simple as its most elegant equations suggest. If the expansion's driver is not a perfect cosmological constant, the horizon might breathe. An equation of state parameter slightly above or below the canonical value of -1 alters the future. A value less than -1 belongs to the so-called phantom regime, where energy density increases as the universe expands. In such a scenario, bound structures could, in an unimaginably distant future, unwind under a scale factor's ruthless acceleration. First clusters, then galaxies, then stellar systems, then, only at the very end, molecules and atoms. The frightening poetry of a big rip is not a prediction but a parameter study, an exploration of what general relativity permits when negative pressure turns aggressive. It serves as a reminder that fate is a function of the fine print in cosmic fluids, and that the end of space may be the end of coherence rather than the end of volume. Another possible end is not stretched but sudden. If the vacuum that permeates the universe is metastable, balanced atop a plateau of energy rather than resting in a true minimum, quantum mechanics allows a transition to a lower state through the nucleation of a bubble that would race outward at nearly the speed of light. Inside the bubble, the constants of nature could differ. The pattern of forces could be rewritten. The wall would be lethal to familiar structures, not because it strikes with intent, but because it redraws what counts as stable. No warning would arrive. Causality ensures that the messenger is the event. The likelihood is unknown, the timescale unanchored. Particle physics has arguments on both sides of stability, but the scenario's existence in the landscape of theory bends the imagination toward humility. The edge of space, if it comes by phase change, is less like a boundary and more like a revision. Topology continues to play the elusive partner. If space wraps, it does so at scales larger than the portion currently drawn within observational command. The absence of matched circles in the microwave background, especially in polarization, pushes the characteristic size of any fundamental cell outward. Yet topology's retreat is not defeat. It is an invitation to consider that finitude without edges may simply be too grand to resolve with available light. The room could be a torus whose opposite walls are separated by distances many times larger than the observable diameter. It could be a dodecahedral jewel whose twist is so gentle that its symmetry hides beneath cosmic variance. In the meantime, hints that once tempted, alignments of low multipoles, cold spots, remain ambiguous, evenly balanced between the lottery of randomness and the faint fingerprints of a global shape. At the smallest scales where theory peers into gravity's grammar, the notion of an edge dissolves further into information. Horizons, black hole or cosmological, carry entropies proportional to their areas, not their volumes, a clue that the bookkeeping of degrees of freedom respects surfaces. Entanglement entropy, a measure of shared quantum information between regions, appears to underwrite geometry itself in several frameworks. The fabric that was once a stage becomes a weave of correlations. In this register, an end of space is not where matter stops but where entanglement is cut. The holographic suggestions that arise from these relations do not yet translate cleanly to a universe like ours, which seems dominated by a mild, positive vacuum energy rather than by the negatively curved worlds where the mathematics is sharpest. But the message is consistent across attempts. Boundaries in physics are often boundaries of information flow. The cosmos may be finite in what can be known, even when it is boundless in what exists. The deepening mystery takes on a practical face in the disquiet between two ways of weighing the same sky. The growth of structure as traced by weak lensing surveys, galaxy clustering, and peculiar velocities can be summarized in parameters that describe how quickly small ripples in density evolve into filaments and knots. Some measurements suggest slightly lower growth than the standard picture predicts when calibrated to early universe constraints, a whisper that either the late-time pull of gravity is gentler than expected or that astrophysical systematics, biases in how galaxies trace mass, complexities in intrinsic alignments, have not yet been tamed. Here, too, speculation and caution share a table. A modified gravity on cosmic scales could soften growth while preserving local tests in the solar system and binary pulsars. An evolving dark energy could tilt the balance between expansion and clumping, or the discrepancy could be a mirage that vanishes when data sets mature. The escalation is not in drama but in precision. As instruments improve, the model is pressed against the edges of its assumptions. Even in the far future imagined by theory, where acceleration has braided a permanent event horizon around local islands, new messengers might alter what counts as knowable. Gravitational waves, less easily scattered than light, sample volumes inaccessible to electromagnetic telescopes. Standard siren measurements, distances inferred from the waveforms of inspiraling compact binaries, already serve as independent rulers. In principle, a civilization that endures could continue adding such rulers to its archive, triangulating the expansion history long after the microwave background has slipped beneath detectability. But even this hope respects the ultimate grammar. If the event horizon has settled, there remain events that no detector can admit. The web becomes less a map than a diary of what passed close enough to be written down. Numbers, once only coordinates, begin to carry the ache of separation. The particle horizon tallies what has ever spoken. The Hubble radius diagnoses the present tempo of recession. The event horizon forecasts a perimeter in the budget of future conversation. These are not synonyms for end, but they exhaust what end can honestly mean in a universe where space is a dynamic participant rather than a container. The escalation, then, is tonal. The cosmos that once seemed an open field now reads like a sentence with clauses that do not all communicate. Punctuation appears in the form of horizons. Meanings depend on which side of a comma an event inhabits. The mystery deepens not because the universe has grown stranger, though it has, but because the language used to describe it has grown rigorous. Early maps of thought asked for a wall. Modern measurements respond with causal geometry, with entanglement, with the thermodynamics of horizons, with small but insistent discrepancies that could be sirens of new physics or stray winds in careful data. Each development tightens the circle around what may be claimed. Each loosens the hope that a single, naive picture, space running out like a shelf, will suffice. He will not find a rim. He will find, instead, a limit on relationships, between regions, between epochs, between signals and their receivers. He will find that as acceleration matures, isolation does not arrive as exile but as definition. He will find that edges, where they exist, are best read in the grammar of information. What can cross, what can never, what no longer can because the universe's expansion has written an ellipsis between speaker and listener. And he will find, above all, that the deepening of the mystery does not diminish its coherence. The equations continue to hold. The maps continue to agree more often than they do not. The surprises are specific, not wild. The question, where does space end, has not been answered with a place, but with a pattern. Horizons layered like transparencies, bending into one another as the future draws its slow, luminous curtain. The search for an edge becomes a study of possibilities, each one a geometry with temperament. In the first family of ideas, the universe is described not by furniture but by curvature, open, flat, or closed, and by how that curvature partners with expansion. An open cosmos carries negative curvature, a saddle spread across 3 dimensions, infinite in extent and without boundary. A flat cosmos stretches like an endless plane, yet even here infinity is not compulsory. Sides can be sewn together quietly so that the room is finite and edgeless. A closed cosmos wears positive curvature, the 3-dimensional analog of a sphere's surface. Finite volume, no rim. None of these geometries offers a wall to touch. Each answers the ancient request for an outside with a reshaping of inside, and with a promise that if a traveler departs in a straight line, the journey's meaning is written by topology, not cliffs. Topology is the second family, a whisper about how space might secretly repeat. In a flat universe, opposite faces may be identified so that a long voyage returns to its origin without ever meeting a border. The 3 torus, a room whose doors open into themselves. In a positively curved world, more elaborate identifications are possible. Among them, the Poincaré dodecahedral space, in which 12 pentagonal faces are paired with a gentle twist. Such spaces are finite yet unbounded, and they hide in plain sight if their fundamental domains are larger than the observable sphere. They would leave signatures, matched circles from light that circle the cosmos along different routes, if the wrap is small enough. The instruments have searched and found no twins at the scales they can resolve. The result is not a verdict of infinity but a constraint. If space repeats, it does so beyond today's horizon of verification. The end of space, in such a world, would not be a place but a pattern that takes too long to reveal. Inflation enlarges the canvas. As a theory of the very early universe, it posits a brief, violent growth spurt driven by a high-energy field whose potential acts like temporary vacuum energy. In this epoch, quantum fluctuations were stretched to astronomical scales, planting the seeds of galaxies and leaving the acoustic watermark later read in the microwave sky. But inflation has a habit. In many models, it does not end everywhere at once. It ends locally here and there while continuing elsewhere, a process called eternal inflation. Where it ends, a bubble universe forms. Where it continues, space keeps swelling. The global picture resembles an endless froth, each bubble a cosmos with its own properties, its own geometry, perhaps even its own constants. In such a landscape, the question, where does space end, becomes contextual. Inside a bubble, horizons and topology set the limits. Globally, space is not a single room but an orchard of rooms growing without a common boundary. Collisions between adjacent bubbles could, in principle, bruise the microwave background with disk-like imprints. Searches have not confirmed such scars, but the possibility remains a reminder that edges may exist as interactions rather than as walls. Dark energy, whether tied to a fundamental constant or to a field that changes in time, governs the far future and therefore the grammar of endings. If it is truly a cosmological constant, as if the vacuum itself carries a tiny, persistent energy, then the universe asymptotes to a de Sitter state. In that limit, an event horizon is fixed by the curvature. Beyond it, events now unfolding can never be known. The end of space becomes an end of conversation, irreversible and thermodynamic. If dark energy evolves, described by an equation of state parameter that departs from the canonical value of -1, fate loosens. A value slightly greater than -1 allows horizons that drift. Slightly less than -1, the phantom regime, accelerates expansion so aggressively that, unimaginably far ahead, gravitational bonds could unspool. In the extremity nicknamed the Big Rip, structure is not carried intact into silence. It is undone by the pace of the scale factor itself. These are branches on a tree rooted in observation. Supernova light curves, the acoustic rulers of galaxies, the polarization of the early sky. None prophesies. Each conditions the future on a parameter that measurements continue to narrow. A different speculation speaks in quantum syllables. If the vacuum that nourishes fields is not perfectly stable, if it balances atop a false minimum, then quantum mechanics allows a lower energy phase to appear in a bubble that expands at near light speed. Inside, the rules might be redrawn, particle masses and couplings might shift, the familiar periodic table could dissolve into a new alphabet. No advanced signal would arrive because the messenger and the event are the same front. Particle physics carries arguments about the vacuum stability that hinge on the masses of known particles measured with exquisite care. Cosmology adds only that, if a phase change is possible, its meaning is a revision rather than a border. In that revision, the end of space is the end of the particular space that shelters familiar structure, replaced by another that does not remember the old. There are frameworks in which geometry itself is not fundamental but emergent, a condensation of relations more primitive than length and angle. In these, horizons are not merely places where light cones pinch. They are measures of information. Black holes, according to the Bekenstein-Hawking relation, carry entropies proportional to their areas. The suggestion, deepened by the thermodynamics of spacetime, is that information counts on surfaces, not in volumes. Extending that idea, the holographic principle posits that the physics within a region can be encoded on its boundary, much like a three-dimensional scene captured on a two-dimensional film. In anti-de Sitter spaces, this correspondence is mathematically sharp. In de Sitter spaces, like a universe with positive vacuum energy, it is more conjectural. Yet the drift is consistent. The ends that matter are informational. A cosmological horizons area becomes a measure of the ignorance imposed by expansion, a budget of what can never be known by any observer confined within. The where of spaces ending dissolves into the what of information that can cross a boundary defined not by bricks, but by causal structure. Entanglement draws the conversation even closer to the weave. Quantum correlations between regions, measured as entanglement entropy, appear in some approaches to be the loom on which geometry is hung. If degrees of freedom are sliced in a certain way, the pattern of their mutual information can, in principle, reconstruct distances. Proposals linking entanglement to wormholes, the ER equals EPR suggestion, argue that connectedness in space may be another face of connectedness in quantum state. If so, then a cut in entanglement is a kind of edge. The boundary between what is correlated and what is not becomes a seam across which geometry thins. This is early language, more metaphor than manual, but it guides the imagination toward edges as failures of relationship rather than failures of substance. The horizon, again, is the visible grammar of what refuses to correlate because expansion forbids exchange. Some models of quantum cosmology seek to remove the beginning's singular edge by transformation rather than by termination. In loop quantum cosmology, the discreteness of quantum geometry modifies the equations near Planck densities, replacing the Big Bang with a bounce. Space contracts to a minimum, then expands. The singular border is rounded by quantum pressure. The Hawking no-boundary proposal performs a different rounding by analytic continuation. The earliest time behaves like another spatial direction, smoothing the starting point into a compact geometry without an initial edge. Neither framework installs a wall. Both reinterpret the question. If the beginning lacks a boundary, the impulse to expect an outer boundary weakens. Space does not so much end as it changes character where classical intuition falters. Modified gravity offers quieter alternatives to the same riddles. If general relativity is not the final grammar on the largest scales, then the inference of dark energy from acceleration might be a misreading. The equations could shift their coefficients in the far field, or new degrees of freedom could slip into the dynamics, altering how geometry and matter converse. These models aim to reconcile late-time behavior, perhaps the mild shortfall in measured growth of structure, with early-time precision without inventing new fluids. They are tested where gravity is both weak and vast, in the slow flow of galaxies along filaments, in the pattern of lensing on the sky, in the rule of how clusters balance their thermal and gravitational energies. If any survive the gauntlet, the implication for edges is indirect but profound. Horizons and fates would be written in a new hand, and what it means for space to end would shift accordingly. Through each of these lenses, the central mystery keeps its silhouette. The universe does not serve a naive edge, even when finite. It offers horizons, mathematical, causal, thermodynamic, that apportion what can be shared between distant regions. It offers topologies that permit loops without outer skin. It offers inflationary landscapes in which the global map is unbounded and diversified, while each local patch is sovereign about its own horizons. It offers quantum grammars in which the most honest boundaries are budgets of information, areas of ignorance that grow or settle as expansion proceeds. It offers revisions, phase changes and modified laws, in which endings are not places but transitions to different regimes of rule. At the margin where mathematics becomes observation, the models are narrowed by data that speak softly but insistently. The acoustic rulers anchoring curvature near flatness, the absence of matched circles at current sensitivity, the measured acceleration that points toward a vacuum-like component, the slow growth of structure that might be slightly slower than expected, the silent agreement of gravitational lensing with large portions of the standard script. What remains open is the global, the wrap of the room, the stability of the vacuum, the deep origin of horizons as thermodynamic or informational truths. In that openness lives the story's force. The question, where does space end, is neither dismissed nor indulged. It is transformed into a family of precise inquiries whose answers, though incomplete, already have shape. He looks outward and the theories become a kind of star chart. Each offers a trajectory, a future, a boundary traced not by stone but by law. In some, the horizon settles like a final punctuation. In others, the page keeps being written just beyond sight. In a few, the alphabet itself is revised mid-sentence. What he learns is not where to sail to find a wall, but how to read the currents that decide which shores can ever speak to which. The edge, if it exists, is a theorem disguised as a view. The question hardens into instrumentation. Horizons, curvatures, and hidden wraps of space are not argued now with metaphors, but with detectors cooled to fractions of a degree and mirrors that drink starlight by the bucket. The modern program is simple in grammar and immense in practice. Trace geometry, time, and topology with rulers that agree from different angles. Listen for faint patterns that should exist if space is shaped a certain way. Repeat every measurement with independent messengers until the answers survive their own cross-examination. On the oldest light, new ears are being tuned. Cosmic microwave background observatories focused on polarization, ground arrays on high plateaus, balloon payloads that rise above weather, and satellites designed for the quiet of space, aim to map the sky with a precision that turns tiny swirls into testimony. Temperature anisotropies have already fixed the broad geometry near flat. Polarization refines it and, crucially, cleans the stage for topology. If the universe is compact, if it wraps with a fundamental cell only a little larger than the observable domain, then matched circles in the sky may be easier to find in polarization, where foregrounds are gentler and statistical noise easier to model. The same polarization data trace lensing by intervening structures. Delensing those maps sharpens what is primordial and what is the fog of later growth. Arrays of transition edge sensors and kinetic inductance detectors, millions of bolometer seconds poured into the sky, try to write an answer in curls finer than chalk dust. Is the room infinite, or merely so large that it only impersonates infinity? Below that ancient surface, the cosmic web is surveyed with rulers grown inside the universe itself. Baryon acoustic oscillations, fossils of sound frozen into the distribution of galaxies, stand as a standard ruler that can be measured again and again from the relatively recent past back to when quasars scribbled the Lyman alpha forest into the spectra of remote light. Multi-object spectrographs comb millions of galaxies and quasars for the faint imprint of the preferred separation. Each detection sketches the distance, redshift relation, and each sketch, when layered upon the others, tests curvature and expansion without asking for any single candle to burn identically across epochs. The same surveys redshift space distortions, anisotropies caused by the peculiar motions of galaxies falling into filaments and clusters, and from these infer the growth rate of structure. Geometry and growth, measured together, test whether gravity on cosmic scales follows general relativity's script or edits its verbs in the margins. Light is also bent into a second language, weak gravitational lensing. Here, the cosmos is weighed not by the glare of stars but by the faint, coherent stretch imprinted on the shapes of distant galaxies as their light crosses the modeled field of mass. Deep, wide images, taken with cameras that see whole degrees of sky at once, measure cosmic shear across billions of galaxies. The corrective work is monastic. Model the point spread function to exquisite detail, calibrate shear biases, assemble photometric redshifts from colors where spectra are impractical, blind the analysis so the human desire to agree with expectation cannot tilt the table. The reward is a map of mass that does not care whether matter shines. When these shear maps are cross-correlated with CMB lensing and with galaxy clustering, a three-dimensional cartography emerges, one that can verify the distance ladder drawn by supernovae and BAO, and test whether late-time growth is subtly slower than the standard model predicts. A slight shortfall could be astrophysics and systematics. It could also be the first toe of new physics stepping across the threshold. Standard candles remain in service, but their candlesticks have multiplied. Type Ia supernovae still trace the acceleration that first announced dark energy, yet the calibration of their absolute brightness is now checked by parallel ladders. Cepheid variables in nearby hosts, tip of the red giant branch stars that offer a population-independent rung, water megamasers orbiting galactic nuclei that measure distances through pure geometry, surface brightness fluctuations in old stellar populations. Time delay cosmography in strongly lensed quasars, where the difference in light travel times across multiple images encodes absolute scale. Each rung, with its own systematics, raises the measurement of the Hubble constant out of a single tradition. Agreement across ladders would calm a present tension. Persistent disagreement would be evidence that the universe refuses to be as simple as the cleanest equations suggest. New messengers arrive with their own rulers. Gravitational waves, space itself ringing when compact objects spiral together and merge, carry a distant scale in their amplitude and their chirp. Paired with a redshift, they become standard sirens, rulers that do not care about the astrophysics of supernova explosions or the dust that dims starlight. When accompanied by light, kilonova afterglows, gamma-ray bursts, or by a statistical host galaxy association, these sirens add points to the distance, redshift curve, and weigh in on the expansion rate. Future space-based detectors, tuned to lower frequencies, will hear supermassive black holes across the deep past and could, in principle, trace the cosmic scale factor without depending on the microwave background. Even in a distant era when the CMB has redshifted into a whisper beyond any practical receiver, the universe might still speak its expansion through gravity's own music. Radio astronomy prepares a separate ledger. Intensity mapping experiments for the 21-centimeter line of neutral hydrogen aim to collect the collective glow of oceans of galaxies, without resolving each wave. In the post-reionization universe, such maps can extend bow measurements over broad redshift ranges efficiently. In the earlier epoch of cosmic dawn and reionization, they promised three-dimensional movies of the first luminous structures carving ionized bubbles into a neutral sea. These films, when cross-correlated with CMB lensing and galaxy surveys, would test the transition between the first structures and the later web, anchoring how quickly the universe's fog lifted. The same data, by opening new redshift windows, anchor geometry when optical surveys thin. Where possible, cosmology seeks direct, patient measurements of time. The redshift drift, the Sandage lobe test, proposes to watch the spectra of faraway objects over decades and to detect an infinitesimal, systematic shift in their redshifts caused by the changing expansion rate. It is an experiment in waiting, a testament to stability in instruments and to the long view of science. Detecting this drift would not merely confirm expansion, already beyond doubt, but would weigh the cosmic acceleration directly in the time domain, a measurement unallied to ladders or standard rulers. If the horizon is a condition of fate, then redshift drift is fate written as a slow verb. All of these grand programs share a quiet spine: metrology. Photometric zero points are chained across hemispheres. Atmospheric seeing is modeled and subtracted. Detector nonlinearity is measured and corrected. Starflat calibrations correct for pixel-to-pixel sensitivity. Spectral energy distributions of standards are tied to laboratory sources. Clock chains keep time at observatories and interferometers with precision that would have embarrassed the 20th century. The question, where does space end, cannot tolerate sloppy measurement, because the answer lives in percent-level differences and in angular features mapped at microkelvin depths. The great campaigns of observation therefore surround themselves with simulations, synthetic skis into which known biases are injected and recovered, mock catalogs that stress pipelines, end-to-end blind challenges that only open their envelopes when analysis is sealed. Topology, elusive in data so far, is pressed in new ways. Beyond matched circles, analysts interrogate the microwave sky's largest modes with statistics crafted to detect multi-connectedness, searches for repeated patterns in harmonic space, Bayesian model comparison among compact manifolds, constraints on the injectivity radius, the smallest loop that space could admit without leaving a trace at current sensitivity. Polarization maps, once complete at the resolution promised, become the decisive court. If no signature appears, the lower bound on the fundamental domain grows. If a whisper of repetition is found, the universe shrinks conceptually overnight, and the ancient dream of a finite yet edgeless world acquires coordinates. Even the future's silence is examined thermodynamically. In accelerating universes, event horizons have temperatures and entropies. Those numbers are not measured directly, but they guide theory. They imply that an observer's accessible patch is a system with a ceiling on information, an insight folded back into forecasts about what future astronomers could recover once the sky's ancient light slides below local backgrounds. Strategic archives, maps, spectra, gravitational wave catalogs, pulsar timing arrays, are imagined as time capsules against that isolating future, repositories that let a later civilization reconstruct a history it can no longer observe. The very act of planning such archives is a scientific test, because it forces clarity about which measurements are fundamental and which are conveniences of a transient window. Across the enterprise runs a culture of cross-checks. Weak lensing shear fields are correlated with galaxy clustering and with CMB lensing. Supernova distances are compared against bow-derived distances. Standard sirens are placed on the same plot. Strong lensing time delays and megamaser disks yield local absolute scales that can be compared with early universe inferences. Where any two methods disagree beyond stated uncertainties, systematics are hunted. Dust laws in supernova hosts, population drift across redshift, intrinsic alignments that mimic shear, selection effects that sculpt catalogs, calibration rungs that flex under scrutiny, each is audited. The edge of space, if it is to be declared a horizon and not a wall, must survive this audit. Not all tools look outward. Some turn inward to the laws. Laboratory efforts measure particle masses and couplings with precision that matters cosmologically. The mass of the Higgs and the top quark bear on the vacuum's stability. Neutrino masses, summed across flavors, leave fingerprints in large-scale structure by suppressing growth on small scales. Axion-like dark matter candidates would alter the matter-power spectrum in ways distinct from cold dark matter. These quantities become priors and posteriors in cosmological inference, tying the sky to the accelerator and the detector under a mountain. If the vacuum is metastable, if neutrinos are heavier than minimal models allow, if dark matter is warmer or self-interacting, the shapes drawn by galaxies and lensing change, and with them, the calibrated distance to horizons. Finally, cosmology practices restraint. Analyses are increasingly blinded. Key numbers are hidden from the teams that reduce data so that choices cannot drift toward cherished answers. Forecasts are made before instruments see light, and then compared with reality to learn whether optimism or caution ruled. Theories are tested with null maps and jackknives, with cross-surveys that share sky but not systematics. The result is not a single verdict, but a narrowing. A space of allowed universes contracting around a picture that is at once generous and austere. Near-flat geometry, accelerated expansion, faint room for curvature, topology pushed beyond current reach, horizons layered by time and fate. In this discipline, the mystery is not dissolved, it is measured. The edge of space is recast as a set of conditions: particle horizon, event horizon, Hubble sphere, each probed by an instrument matched to its tense. The question becomes a network of experiments: microwave polarization that hunts topology, galaxy surveys that weigh curvature and growth, weak lensing that maps mass directly, supernovae and time delays that pace expansion, gravitational waves that supply independent rulers, radio intensity mapping that opens new redshift windows, patient spectroscopy that waits for the universe to change its own numbers. If there is a wall, none of these will touch it. If there is not, all of these will still have answered the only version of the question that physics can honor. How far can events exchange information, and what geometry and law decide that distance? He stands inside a grammar instead of a wall. By now the lesson is steady. Space does not end the way a country ends or a shoreline ends. It ends only in the sense that conversations end, when voices cannot cross a distance defined not by miles but by law. Horizons appear as punctuation in a sentence that keeps being written, a particle horizon that marks all that has ever spoken to the present, a Hubble sphere that diagnoses the tempo, an event horizon that, if dark energy holds dominion, draws a permanent clause around what can ever be shared. The cosmos is not a box, it is a relation. It does not run out, it becomes quiet. He considers how small his era is against the patience of the sky. Star formation is still ongoing, yet most of the hydrogen that will ever be turned into stars is already spoken for. On timescales that human language can scarcely respect, galaxies exhaust their fuel, new stars dwindle, the bright epoch dims. If acceleration persists, only the local island, galaxies already bound by gravity, remains a commonwealth. Far beyond that island, the filaments continue but slip irretrievably across the event horizon, their light forever incomplete. The end that poets once placed at the rim of the world reappears as a limit on sympathy. Regions that once could have conversed grow unable to. The sky withdraws not by collapsing, but by becoming unable to speak across its own expansion. He remembers that horizons are not emptiness. In general relativity, they have thermodynamics. In quantum theory, they acquire temperature and entropy. A black hole's boundary carries an entropy proportional to its area. A cosmological horizon in a de Sitter phase does likewise, with a faint temperature set by the expansion rate. The message is austere and consoling at once. Boundaries in the deep grammar of physics are measures of information, not fences of matter. A horizon is a statement about what can be known, not about what exists. The end of space, if he insists on the phrase, is a budget of ignorance written onto the sky by expansion and curvature. There is humility in that budget. Even within his own island, the archive will thin. The cosmic microwave background, the oldest light, the photograph of the universe when it turned transparent, cools as the scale factor grows and eventually redshifts beneath practical notice. Future astronomers, if they endure, will read their history through other messengers. Gravitational waves from far mergers, the fossil kinematics of stars locked in ancient orbits, the chemistry of old atmospheres on planets that outlived their suns. They will build their cosmologies from what remains inside the horizon's book. Their answers will differ only where evidence has been sealed away by expansion. The universe is impartial. It lets each epoch learn what it can. He thinks of Kant's antinomies, those tidy arguments that space must be infinite and must be finite, both proved with equal rigor and thus both signaling a limit of reason. Physics did not overthrow those antinomies. It rephrased them. It showed that finite yet unbounded is not a paradox but a manifold. That infinite is a statement about topology as much as about measurement, that either condition can be consistent with the same local geometry. The old question remains beautiful, but its best answers are now operational. Does space end? It ends where signals cannot arrive. Is space infinite? The largest maps say it is nearly flat and perhaps compact, but if it wraps, the wrapping lies beyond his present horizon of verification. The proper mood is not triumph but clarity. The mind was not wrong to ask for a wall. It was early. The old paradox of the dark night yields a similar solace. Auber's complaint that an infinite, ageless, uniform universe should produce a sky blazing as the surface of a star dissolves in history and expansion. Stars are not ageless. The cosmos is not infinitely old. Light redshifts and dusk glows imperfectly. Darkness is not evidence of an outer void. It is a record of time. In such revisions he finds a pattern. Naive infinities replaced by finite ages, edges replaced by horizons, places replaced by relations. The cosmos has not grown smaller. It has grown articulate. He lets the speculative branches pass before him without hurry. Inflation that keeps a global canvas inflating while local bubbles, like his, exit into their own laws. Vacuum metastability that could revise the alphabet of physics in a bubble expanding at near light speed. Equations of state that, if pushed below -1, would unwind structure in a distant future where even atoms lose their coherence. None of these is prophecy. Each is permission granted by equations tested in other domains, conditioned by measurements that are precise but not yet final. They serve as reminders that an end may be a transformation rather than a boundary. What changes, if it changes, will be the meaning of connection, the grammar by which regions, particles, and histories remain in relation. He notices, too, the counterpoint, attempts to show that geometry is not fundamental but emergent, that spacetime is the coarse-grained face of quantum entanglement. In such approaches, distance is reconstructed from patterns of shared information. Wormholes become metaphors, sometimes more, for entanglement itself. If that is right in any durable sense, then the most honest answer to his question is sharper than he first believed. Space ends where entanglement ends. A boundary is a cut in correlation, a failure to share state across a divide. The cosmological horizon, then, is not a shell of silence in a literal sense, but a frontier across which correlations cannot be refreshed. Everything beyond it may exist richly. It is only the relation that has failed. He sees the human scale reflected in these laws. Civilization, any civilization, lives amid horizons as surely as it lives amid seasons. It inherits a finite archive, contributes to it, and hands it forward down a narrowing corridor. Its instruments lengthen perception. Its mathematics extends intuition. Its philosophy patrols the borders with questions whose answers return as modest truths rather than monuments. Meaning under such conditions becomes local and relational, an excellence of craft in measurement, a discipline in inference, a generosity in doubt. In a cosmos without a rim, purpose finds itself in tending the small island of communication that physics permits. He lets the future roll forward. Stars like the sun swell and redden, shed envelopes, leave white embers that cool in the dark. Supermassive black holes in the hearts of galaxies bind and sometimes merge, ringing spacetime with waves that carry distances on their backs. Evaporation begins, only in timescales that mock clocks, hawking radiation leaking energy slowly from horizons that once seemed perfect prisons. If protons decay, matter thins even where gravitational vaults keep it safe. If they do not, matter remains stubborn in its simplest bricks. Theories divide, observations differ, the story proceeds either way. In the very long end, the cosmic acceleration leaves each island enclosed by its own event horizon. The universe is populous, yet every archipelago is alone. The mood at this point could turn bleak. He refuses it. The silence beyond a horizon is not an indictment of the world. It is the condition that makes any knowledge possible at all. Causal structure, the cones that decide what can influence what, saves physics from paradox. Thermodynamics at horizons, from black holes to de Sitter skis, saves information from miracle by giving it a price. The success of simple rulers, acoustic peaks frozen into the microwave background, baryon oscillations in the galaxy web, the chirps of merging binaries, saves cosmology from storytelling by tying it to things the world has written in light and gravity. He finds a kind of grace in these constraints. The universe enforces humility and rewards patience. It does not bend to appetite. It answers only to questions it can honor. He returns briefly to the beginning, because beginnings and endings collaborate. If the Big Bang's singularity is an artifact to be rounded, by a bounce in quantum geometry or by a no-boundary smoothness that replaces a sharp start with a rounded cap, then edges in time yield to changes in character. The same may hold outward. If there is any end, it is not where things stop existing, but where the category mutual influence stops applying. The symmetry he sought is one of attitude. At both ends, the correct language shifts from nouns to verbs, from places to relations, from surfaces to conditions. He looks once more at a night sky whose photons left before his species learned its grammar. The question that set him walking, where does space end, has been translated beyond recognition and yet remains intact. It has become, how far can events be braided into a common history? What geometry and law set that distance? What becomes of meaning when that distance contracts or expands? These he can answer with numbers, with uncertainties, with forecasts pinned to conditions. The wall he once imagined was a shape. The edge he has found is a principle. He stands then, not at a rim, but at a threshold of understanding, the kind that moves as he moves. The cosmos is not less mysterious for having been measured. It is more exacting. Its mystery has migrated from what lies beyond a fence to why fences of information arise at all, to how geometry and entanglement conspire to make a world in which islands are possible. The camera could rise now, pulling away from him into the dark, the filaments thinning into a fog, the fog into a black that is not emptiness but depth. The narration could quiet. He would remain, a thinker among instruments, an island among horizons, learning to read a universe that declined to give him an end and gave him, instead, a language.